Building information modeling is everywhere in today's architecture and construction industry, yet projects are still failing, crippled by coordination conflicts and massive rework. Industry data suggests a recurring pattern. Teams are often prioritizing the visual polish of a 3D model over the integrity of the data behind it. Look at this ISO 19650 framework. The geometry dissolves, revealing what BIM actually is: a strictly structured, information-driven network. When verified data routes safely down this decision tree, operational risk drops. Information flow dictates if a project survives schedule and budget constraints. To understand why modern sites still face collapses, we must forensically investigate 12 vulnerabilities across 4 key domains: data, handover, coordination, and execution. Failing to address these weaknesses ensures a single data entry error in an office multiplies into a catastrophic delay on the concrete slab. The pipeline breaks down first at the source. This is the data quality failure. This diagram shows an HVAC chiller unit stripped to expose BIM metadata. When fields for specifications and asset tags are left empty, the geometry becomes useless. Notice how empty fields propagate downward. Missing data here contaminates structural and electrical systems below, leading to coordination errors. This contamination often starts when project teams treat the BIM execution plan as a static compliance document, rather than a daily operational workflow. We map this on an ISO 19650 responsibility matrix. Flashing unassigned intersections represent entry points for unverified data. To stabilize the system, these points must be locked down. Strict naming conventions and validation workflows force every piece of information to be verified before use. Without this verified data foundation, a meticulously detailed 3D model functions as a project liability rather than an asset. To measure why that data foundation matters, we must look to the end of the project. The final product of digital construction is the facility handover. This illustration shows a common handover failure. A pristine digital model is delivered, but the data pipeline is severed because the model lacks verified as-built conditions and crucial operations and maintenance information. The owner now possesses a physical facility they cannot operate digitally, forcing them to fund a manual rebuild of the data they already paid for. To prevent this, the industry relies on the level of information need, or LOIN. This timeline shows a slider dynamically adjusting the data depth attached to a component. As it locks into the handover stage, the data block expands to reveal verified as-built metrics. A successful LOD 500 delivery requires a validated COBie dataset, functioning within an asset information model, as defined by the National Institute of Building Sciences. If the final digital model cannot be used for daily operations, the digital objectives of the construction phase have simply not been met. Bridging the gap between initial data entry and final handover requires a mechanical engine: coordination. This illustrates a common data environment failure. Outdated file paths bypass the central CDE vault and feed directly to the site, triggering a structural clash running. The fix requires control. Bypass paths are severed, forcing all data through the vault for approved revision stamping. Even with version control, poor model coordination causes delays. When clash detection is executed late or without discipline, physical conflicts are shipped directly to the job site. Teams must utilize tools like Autodesk Navisworks to establish strict spatial tolerances, executing weekly clash resolution routines to eliminate conflicts before components are ordered. This process establishes a mandatory rule: 2D shop drawings must only be extracted from fully approved, perfectly coordinated 3D models. Without a single source of truth and rigorous clash detection, the workflow merely formalizes construction errors on paper. We finally arrive at physical site execution, where the digital twin often detaches from ground reality. Look at this illustration of the operational silo. An isolated BIM team is separated by a deep chasm from the actual construction site, where workers are relying entirely on crumpled 2D blueprints. A coordinated model holds no value if the site crews ignore it when developing their method statements and daily coordination plans. This chasm is often maintained by unstructured communication loops between the BIM modelers in the office, the engineering consultants, and the site contractors. Bridging this gap requires a structural link: structured request for information data packets, moving continuously from site nodes back into the central BIM model. As these RFI packets hit the database, connected 2D floor plans dynamically update, ensuring the model reflects physical site realities. A digital model detached from the site functions as a storage-heavy archive, offering no practical utility to the crews on the ground. The success of a digital construction project balances on three interdependent pillars: data quality, coordination, and handover. This macro view shows when vulnerabilities are patched. Verified data nodes feed a clash-free coordination engine, filtering into precise site execution. But observe the fragility. If one data node fails and turns red, a cascade of failure warnings rips through the entire downstream pipeline. Governing standards like ISO 19650 and Building Smart provide the technical specifications required to maintain a functional firewall against that cascade of failure. By enforcing these rules, contractors align their digital and physical workflows, facilitating precise real-world construction execution at scale. Prioritizing the information over the geometry realigns the digital model with the physical site, establishing a reliable map for the entire project lifecycle.